3 on concavity points of inflection. We're going to start off here with example 5 on our notes. Quite honestly, if you can do this problem, that means you understand basically this entire unit up to this point. I've given you one function, f of x equals x cubed minus 4x, and we're finding everything about it. Intervals of increase and decrease, intervals of concave up and concave down, which we have not formally done yet, as well as local extreme values, so that'll be maximums and minimums, and inflection points. A, B, and E are going to go together, and C, D, and F are going to go together. So I'm going to start with A, B, and E, because I really kind of have to get through those before I can get to the other three. So intervals of increase and decrease and extreme values, remember those are going to come from the first derivative. So first thing we need to do is actually find the first derivative. So it would be 3x squared minus 4. Then we would be looking for where does this guy equal 0 or not exist. It's a quadratic, it has no domain restriction, so it exists everywhere. So all I'm concerned with now is where does it equal 0. So we end up with x equals plus or minus the square root of 4/3, which would be 2 over the square root of 3. So those are the critical points, which means they might be where I have extreme values. So I'm now going to create a sign line for my first derivative, and then I'm going to label it with an f pointing out to the side. I'm going to put negative 2 over the square root of 3 and positive 2 over the square root of 3. And then I'm just going to choose a number for each of those intervals. So for my first interval, that number I know would be, if it was positive, would be smaller than 2. I'm safe with choosing negative 2 to go in that first interval. So that would be 3 times negative 2 squared minus 4. Negative 2 squared is 4, times 3 is 12, minus 4 is 8, which is a positive number. Okay? In my next interval, because I go from a negative critical point to a positive critical point, that would come to be 0 in my next interval. So 3 times 0 is going to be 0 minus 4 is going to be a negative number. And then in my last interval, I'm going to use positive 2. So 3 times 2 squared is 12 minus 4 is a positive number. So I can tell three things from here. I can tell where my graph is increasing, I can tell where my graph is decreasing, and I can tell which points are maximum and which are minimum. So going back up here, reading straight off my sign line starts at negative infinity and ends at positive infinity. So any part of my sign line I've marked as positive would be where my original graph is increasing. Any part that I've marked as negative would be where my original graph is decreasing. And I actually have two sections of my sign line that are marked with plus signs. So I have two intervals of my original graph where it would be increasing. The other thing I know are the local extreme values. My original graph would increase, decrease, increase again. So that would tell me that negative 2 over the square root of 3 would be a local max. The x-coordinate is negative 2 over square root of 3, so to get the y-coordinate, I would substitute into the original function. And I'll go ahead and cut to the chase and tell you that that is 16 square root of 3 over 9. And then you would have a local minimum at positive 2 over the square root of 3, and its y-coordinate is negative 16 square root of 3 over 9. So that takes care of the information I can get from my first derivative. So now I'm going to move to the second derivative, which means I need to take the derivative of the first derivative. It is 6x. It's going to exist everywhere, no domain restriction. So all I care about is when it equals 0. That would be at x equals 0. So now I'm going to make a sign line for my second derivative, and the only value on it is when x is 0. So if I pick a number to the left, let's say negative 1, and substitute it into my second derivative, I would get a negative number. And if I substitute, say, a positive 1 to the other side, I would get a positive number. So that tells me three things. Any place where the second derivative sign line is positive is where your original graph is concave up. And then any place where the second derivative sign line is negative is where the original graph would be concave down. So if I read my timeline from negative infinity to positive infinity, I would be concave down from negative infinity to 0 and concave up from 0 to infinity. That also tells me that my inflection point is at an x coordinate of 0, and then I would just substitute that into my original function to get the y coordinate, which would also be 0. This would make a great FRQ on a test or on the AP exam because it covers a whole lot all in one thing there. So don't be surprised if you see something like this. In fact, I'd be almost going to put money on the fact that you will see some type of graphs FRQ on the AP exam. So that's example 5. Example 6 would also make a great FRQ, but notice the information has changed a little bit. This time they didn't give us the f of x function. They've given us f prime of x is 4x cubed minus 12x squared. And they want us to find the extrema, the intervals on which the function is increasing and decreasing, where it's concave up and down, and then sketch a graph. So this covers all the bases too. This would make a great FRQ. So for identifying the extrema and intervals of increase and decrease, all that comes from the first derivative, which we already have. So I would start with where does it equal 0 or does not exist. It's a cubic, so it exists everywhere. So all I'm concerned with is where it equals 0. This way you can factor. You can factor 4x squared out of them. That's times 3. Now, 4x squared does not disappear. We get set equal to 0 just like the x minus 3x. So we get x squared equals 0, so x equals 0, and x equals 3. So our two critical points are x equals 0 and x equals 3. We would then create a sign line for the first derivative and substitute numbers from each of those intervals into the first derivative. So for example, -1. And we would get -4 minus 12, so we would get a negative number for the first interval. Maybe I'll try positive 1. And we would end up with 4 minus 12, which is also a negative number. That tells me that I do not have a maximum min at 0 because I decrease and I continue to decrease some more. And then that is 4. We would end up with 4 times 64, and then we would subtract from that 12 times 16, and we would end with 256 minus 192, which would be a positive number. So the derivative does actually change signs at 3. So what that tells me, going back up here, the extrema would occur at x equals 3. Notice I can't give you a y coordinate because I don't have an original function to substitute 3 into. So the best you can do there is to give the x coordinate. The intervals for the increase and decrease, I can read that straight off of my first derivative sign line, and I'm just kind of cramming it in here for lack of space, but you would want to make it more organized on your paper. We would be increasing from 3 to infinity, and then we are decreasing from negative infinity all the way to positive 3. Even though we had that stop along the way at 0, we continue to be decreasing there, so we can just kind of glide right past it. So now for the concavity, we will need the second derivative. So I'm going to take the derivative of f prime, and so we would get 12x squared minus 24x. And it's a quadratic, so it exists everywhere, so we're just concerned with where it equals 0. You can factor 12x out of that. The 12x does not disappear. It is a factor as well because it has an x in it. So they both get set equals 0, we get x equals 0, x equals 2. So now we'll do a sign line with 0 and 2 for the second derivative. So maybe I choose -1 in the first interval. Notice we're going to substitute it into the second derivative now. I would get 12 times 1 is 12 plus 24, so we would get a positive number in the first section. So I use positive 1 for the next. I have 12 minus 24, which is negative. And then I use positive 3 You get 12 times 9 is 108, minus 24 times 3 is 72. 108 minus 72 is going to be positive. So I do change signs every single time on the second derivative graph. So concave up would be negative infinity to 0 and 2 to positive infinity. And then concave down would be 0 to 2. Now part D, for sketching a possible graph. This kind of goes back to what we did at the very beginning where we had the chart with the four different curves and kind of piecing them together. So I need to pay attention to not only the intervals where the function is increasing and decreasing, but also the curvature based on whether it's concave up or concave down there. So I know that I have an extreme value at x equals 3. Because my graph is decreasing and decreasing until I get to x equals 3, I know it's going to be a minimum. So I'm going to just, mark off x equals 3 and go ahead and just put myself a minimum point there. So basically, the other things I know are that x equals 0 and x equals 2 are going to be points of inflection, where my concavity changes. So my graph is now chopped up into those different sections of my concavity. From negative infinity to 0, I'll be concave up, but I should also be decreasing. So decreasing and concave up, I'm going to switch to green so that it doesn't kind of overlap with already here. So decreasing and concave up all the way until x is 0. So it could be something like that. Then from 0 to 2, I should be concave down. However, based off my first derivative, 0 to 2 is still in this decreasing interval. So decreasing and concave down might look something like that. My next little section would go from that point of inflection at 2 until the minimum at 3. 2 to 3 is in the concave up, but it's also still in the decreasing. So decreasing, concave up. So it would look maybe something like that. And then from 3 to infinity, I'll begin increasing, and I'm also concave up. So the whole rest of my graph could look something like this. Yours doesn't have to look exactly like mine, but you should have 4 curves that are similar to my 4 chunks of curves. All right, so that wraps up example 6. I'm going to make one more short video for example 7 that I encourage you to watch.